Hello, it's a video on matrices and transformations. We've got three types of transformation here we're going to look at: stretches, reflections and rotations. The key connection is what I've written here in this box. That if I take an object vector and then I multiply it by the matrix, I get the image of that object, yeah? And therefore if I do that for all the points, I get an image of the whole object that we're looking at. So that's our matrix algebra format of what we're doing here. Okay, what I'm going to do in the first video is just look at a number of transformation matrices, and in the second video I'm going to look at creating matrices from unit vectors. I'm also going to look at playing around with matrices rotation to create some new rules. Okay, let's start off with a stretch then. Here's a matrix, and if I apply this matrix to the point 2, 1, what do I get? Well, here's the matrix, there's 2, 1, multiplying using matrix operations, what do I get? I get an x value of 6 and I get a y value of 1, yeah, 6, 1. So I've moved this point to there, and probably just looking at the diagram you can see that that's a stretch in the x direction, scale factor 3. Nothing happened to the y, did it? Let's just check that out by taking the matrix and multiplying it by the general point xy, and what do I get? I get 3 times 0 gives me 3x. 30xy gives me 3x on the top, and gives me 0 1 times xy gives me 1y on the bottom. So the y is unchanged. I've written it as 1y just so you can see there is actually a scale factor there, but it's 1. So the y is unchanged and the x has stretched the x direction by scale factor 3. So if I were to generalize that approach, then this is a generalized stretch matrix, and up here in the top left we have the scale factor in the x direction, and down here we have the scale factor in the y direction. So in the example we just looked at, we had a 3 and a 1. We could have different scale factors there, couldn't we? So we could have a combined transformation with one stretch for say 3 in the x direction and 2 in the y direction. Now the other thing we could do is if these two are actually the same, say they were both 3, we'd be looking at an enlargement, wouldn't we? The other thing to bear in mind is all of these are stretches, and if we had an enlargement we're looking at around the origin, aren't we? Yeah, and the x and y axes. So that's stretch matrices. Let's have a look at some reflection matrices. There's one here. So let's see what happens. If we take that matrix and we take the point 2, 1 over here and we multiply that out, what do we get? Well, we get the point 1, 2, which is over here, isn't it? So that's starting to tell us that we're probably looking at a x equals y reflection. But let's just check that out. If I take the matrix and I multiply it by the generalized point xy, what I get out of this as the image is yx. Yeah, so that's a reflection in the y-axis. Let's have a look at some other reflections. Let's have a simple matrix, this one here, 1, 0, 0 minus 1, and if we multiply that by xy we get x minus y. So therefore the point 2, 1 would become the image of it would be the point 2 minus 1. So what we're looking at, well, we're looking at a reflection in the x-axis, or y equals 0. And of course if we wanted to look at the matrix minus 1, 0, 0, plus 1, yeah, there we go, and we did that with xy, we would get the point minus xy, which would be a reflection in x equals 0, wouldn't it? Or in the y-axis, yeah, there we go. So those are our two basic ones, and just one more extended one here in reflections. Let's have a look at the reflection. If we looked at this matrix here, 0 minus 1 minus 1 0, and if we multiplied that one out, there's the matrix, there's x general xy point, we get minus y minus x. So the point 2, 1 would end up at the point minus 1, 2. So that's a reflection in y equals minus x. Now we can find the reflection in any line with any gradient, any line that's going through the origin, must go through the origin for this to work. But we can come back and work on that in class. Okay, next one, rotations. Here's a matrix. Cos theta sine theta minus sine theta cos theta. So there's the matrix. And I'm going to look at what happened to the points 1, 0 and 0, 1. I'm going to do that for a reason, because it's going to help us look at what we've got here. So if I take the point 1, 0 and I multiply it by this matrix, well, I end up with the point cos theta sine theta. So if I were just looking on my little diagram here, that was started at 1, 0, my point P, and I end up here at cos theta sine theta. Well, most of you will recognise that as being a little right angled triangle. It's got the hypotenuse length is 1. We've got an angle of theta here, haven't we? So that's going to be cos theta, and that's going to be sine theta there, isn't it? And what happens if I take the point 0, 1 and I multiply that? Well, I get the point minus sine theta cos theta. So if I started here at Q, I end up over here at Q dash. Here we go. And again, if I draw I'll get a little right angle triangle. It's got an angle theta, and it's got a hypotenuse length of 1. So that's what happens to our 2 points. So what are we looking here at? A transformation? We're looking at a rotation. We're looking at an anti-clockwise rotation, and we're looking at an angle of theta, and we're also looking at one that's around the origin. So all these rotations are around the origin. So you're starting to see a pattern here that all of these only work if we're looking around the origin. So here we are. Just a quick summary for you for the first half is that what we've got here is a series of matrices that do stretches, they do reflections, and they do rotations. They do not do translations. Yeah, we don't get translations here. And the reason for that is because we're doing lots of multiplication here. Our origin 0, 0 always maps to, always transforms to 0, 0. Yeah, because we're always doing multiplications, not additions. And in the next video, we're going to look at how we can create the matrices and how we can use them. But I thought it'd be useful to stop at that point and see where we are.